Hello, everyone. Welcome to Lesson 5 AI Problem Solving Methods. So, this week we are going to focus on data structures. Um, let's look back at our previous lesson 2, 3, and 4. We talked about intelligent agents, how AI solves problems using search, and various search techniques. Think of those as the strategies. So today is about the tools we use to execute those strategies. So the heart of today's lesson is data structures used in AI programs. Now, you can't build a house without knowing your materials. Similarly, you can't build AI without understanding these structures. So by the end of this class, you'll be able to explain why AI needs special structures, identify the core ones, match them to specific AI tasks, and understand the trade-offs in efficiency. We want to recognize which structure work best for search, machine learning, and knowledge representation. So why is AI different? Conventional programs follow a straight line. AI programs are different because they explore huge search spaces. They represent knowledge using symbols. They handle uncertainty, that is the maybes of life, and they learn from data. Because of these, we need structured, relationship aware, and probabilistic models. So, data structures matter because they allow AI to represent states, that is where we are now, and explore search spaces, that is where we could go, to us, and also to store knowledge and support learning. Without these, the AI would be blind and forgetful. So let's categorize our tools into four buckets. So we have graphs and trees for relationships. We have matrices, vectors, and tensors for numbers and math. We have logic sets and rules for symbolic thinking. And we have operational structures to make everything run fast. So graphs and trees are the most common. We use directed graphs for flow, undirected graphs for connections, trees for making decisions. We use search graphs to find path, like a GPS finding the best route. So let's look at directed graphs. Think of making a cake. You buy ingredients, you mix, you bake, you decorate, you eat. You can't go backward. It shows a clear cause and effect. Undirected graphs, on the other hand, are different. They think of a group chat with friends. Everyone is connected equally. So if I share news, everyone sees it. There's no single direction of flow. It's about mutual influence. Now look at trees. These are perfect for decision trees. If it's raining, take an umbrella. Or game trees, predicting your opponent's next move in chess. A parse tree for natural language breaks down sentences into grammatical parts. Search graphs or state spaces are what we use when an AI is trying to solve a puzzle or navigate a maze. Every node is a possible position, and every edge is a move the AI can make. So A is the source node, that is the starting point. B, C, D are intermediate nodes. X1 and X2 are sink or terminal nodes. The numbers in parentheses represent the capacity and the cost, where capacity could be the distance in kilometer, the cost could be the amount in thousands of naira. So to go to X1, the the AI could move from A to B to X1, or A to C to X1, or A to D to C to X1. So those are the possibilities to go to X1. So for it to optimize the paths, if distance is your priority, you want the shortest possible path, you know that you can do the mathematics by adding up the first uh, number in the pair. So from A to X1 via B is going to be 5 plus 4, which is 9. From A to X1 through C is going to be 10 plus 3, which is 13. That is longer. Going through D is going to be 2 plus 1 plus 3, which is 6, which appears to be the shortest path. So that's how the mathematics is made. If you are interested in cost, you add the second numbers. So going from A via B to X1, the cost is 3 plus 6, which is 9,000 naira if it's in thousands. Going from A to X1 via C, the cost is 4 plus 1, which is 5,000 naira. Then going from A to D to C to X1, the cost is 6 plus 4 plus 1, which is 11,000 naira. So that is how the search graph and state spaces work. So finally, in this section, we have factor graph and temporal graphs. These are advanced tools for when relationships change over time or involve complex math dependencies. Now we move to math side, that is matrices, vectors, and tensors. These are the tools for statistical learning and modern neural networks. A vector is just a simple one-dimensional list of numbers. It represents both magnitude and direction. In AI, we use it for feature sets, like like the characteristics of a house, for example. So the features are the elements of that dimension. For example, a house vector might look like 321500, representing 3 bedrooms, 2 bathrooms, and 1,500 square feet. We multiply this by weights to predict the house price. Okay, so let us see what's going on with this vector sample Python code. Now, the code predicts the price of a house based on the number of bedrooms, the number of bathrooms, and the square footage. That is the size uh, of the house. It uses a feature vector, which is the house details, a weight vector, which is how important each detail is. So the weight vector is telling us each of those details, how important it is. Then a dot product, which is a math operation that combines them. So this is actually a very simplified version of how machine learning models make predictions. I'm taking time to explain this because in this entire course, we will not have the time to go into machine learning. So for those of us who do not know how machine learning models work, if you pay careful attention, you will understand through this example how machine learning models make predictions. So let's look at the code line by line. So we have import numpy as np. Numpy, numpy is a Python library used for math and arrays. So we are renaming it as NP to make typing shorter and to prevent namespace conflict with functions. This line, house underscore features, this is a variable, right? Which takes in a vector, which is a list of numbers. So this function, this command creates the vector, which is stored in this variable called house feature. So anywhere we see house features, it's the vector that contains the 3 features: bedroom, bathroom, and square footage. So this is referred to as the feature vector, which holds the input information. Okay. Now this other one is also a variable, which is the weight vector. It contains number for each of the features, telling us how important it is. So for this, it has 50,000. It's a weight telling us how important that the bedroom is the most important of all this, because this is what people really look at. They want to know whether it's a 3 bedroom flat, is it a 2 bedroom flat, is it a 4 bedroom flat, is it a 1 bedroom flat. That is what even determines whether someone will buy that property or not. That's the first thing. And because it's so important, it carries the main weight. So the bathroom, the number of bathrooms, well, yes, it's important. Some people prefer 2, 3 bathrooms. Some we want en suites, each bathroom to be in each of the rooms. So so it depends. But however, the bedroom carries the highest weight. followed by the bathroom, and then the square foot. Well, people, some depending on the location, like in Anambra State now, we agreed that Onitsha has the highest property value compared to somewhere like Abagana. You will be surprised that property in Abagana, people will be very concerned about how big the house is. You discover that in a place like Abagana, where um, properties are cheaper, people will the value for the square foot will be higher because people want bigger houses. But in Onitsha, nobody cares about how big the house is. They just want to be near, it's a highly commercial area. So the size of the square footage doesn't matter to them. That's why the weight is small. Even you'll be surprised that a very small square feet house, a very small house in Onitsha, maybe 10 times more expensive or 5 times more expensive than the same square footage of house in Abagana. Okay, so that's where this weight comes in. Now, how do we get this weight? The machine or the AI model learns it from data. So maybe you've already provided the prices of 1,000 houses in Abagana and the prices of 1,000 houses in Onitsha. Based on those prices, the machine will fix the weights itself and use it in predicting the prices of houses in those two regions. So now this is where the dot product comes in. That dot product is very easy, just normal matrix, normal multiplication of two vectors. So it's going to look like something like this. It's going to look like something like this. So we have 3 times 500 plus 2 times 2,500 plus 1,500 times 200. So this height looks like for the dot multiplication. It's a simple dot multiplication of two vectors. And so this is the total we get for the house. And I think it's in dollars because I don't think in Nigeria you get any house 500,000 naira. So the prediction is equal to the features times the weight. So machine learning often works by turning real world information into numbers, which are features. Then it now learns how important each feature is, which is the weights. It now multiplies and adds them together to make a prediction, as simple as ABC. It's used in house price prediction, credit scoring, recommendation systems, basic AI models. Okay, so it's very, very, very important. So for the weights, let's see. Let's see uh, an hypothetical example for both um, Abagana and Onitsha. Okay, so now look at the sample two data sets of houses prices in Abagana and in Onitsha. These data, let's assume that the data for Abagana is up to 1,000 or maybe 5,000, depending. And the one for Onitsha is like 5,000 too, or maybe 1,000, but quite a reasonable amount of data. These two data sets that has the prices already of existing property in these two locations. These two data sets is called they are called training data. The accuracy of your machine learning model depends on the quality of the training data. So as long as the training data they are accurate, then your model would have a high accuracy. So what the model sees here now is house features, bedroom, the number of bedrooms, the number of bathrooms, the number of square foot, and the real prices of existing property. Then the duty of the model is to see how it can make a connection between the prices and the features. Now I want you to pause and study these two data carefully. You can see that the bedroom, the bathroom, the square feet for both Abagana and Onitsha, they are the same. But the prices are different because one is in a prime area, another is in a non-prime area. Now let's see how the model learns the weights. It's very, very important. Once you understand this, you understand how machine learning model works. So how does the model learn those weights that makes it able to predict almost accurately, sometimes even with almost 100% accuracy? So let's look at Abagana. It looks at this and says, okay, what um, what can I use to multiply to the bedroom, the bathroom, and the footage, add them together to give me 18 million for the first. So what can I use to multiply to and add it to the multiplication of one with another weight, add it to the multiplication of 900 with another weight to give me 18 million. So it's going to start off So let us assume a very simple linear model where the price is the beds, number of bedroom multiplied by the weight for bedroom plus the number of bathroom multiplied by the weight for bathroom plus the number of square feet multiplied by the weight for square feet. So WB, WBA, and WS are the weights the model must learn. Okay? So the next step, the model starts with random guesses. So for the bedroom, it suggests a weight of like 1 million. For the bathroom, 1 million. For the square footage, 5,000. Now, these are just starting guesses and probably wrong. So using those weights for the first row, it tries to make a prediction by multiplying them with the weights as shown below. The predicted value for a house is 7,500,000. But the actual price is 18 million and the prediction is 7.5, which is quite low. It will try for the second row using the same weight, and the value is 12.5 million, which is quite far from the actual value of 50 million. So it's very wrong again. So the model attempts to measure the error, and the error equals actual error minus predicted minus the error equals the actual value minus the predicted value. So for example, for the second row, the actual value was 50, the actual value is 50 million, the predicted value was 12.5 million, and then the error is 37,500,000. So the model knows 37,500,000. The model knows that its weights are too small and is underpricing houses. So the algorithm increases weight slightly, try prediction again for the rows, and discovers that well, it's slightly higher than the previous one. So the error has been reduced, which is an improvement. So the loop continues. It predicts, compute error, adjusts weights, and repeats. Each round moves weights closer to correct values. It could do this over 1,000 times or less. Now, this is called training. So, this is not a guesswork. It's not about, I think a bedroom is worth 10 million. No, the model says from actual sales data, bedrooms contribute about 9.5 million. So, data decides, not opinion, not guesswork. A matrix is a 2D grid of numbers, rows, and columns. So, think of it as a collection of vectors. In machine learning, rows usually represent different samples, like different students, and columns represent features, like their grades. So why use matrices? Because they allow for vectorized operations. Instead of calculating one student's grade at a time, we can calculate everyone's final score at once, which is much faster for a computer. Tensors are high-dimensional grids. A 3D tensor could be a color image like height by width by color channels. A 4D tensor might be a video, which is a batch of images over time. These are the standard containers for data in frameworks like PyTorch and TensorFlow. Now consider a grayscale video. It's a 3D tensor made up of a stack of black and white images, which are frames. So if the video is 10 seconds long at 30 frames per second, that is 300 images stacked together. So you see them as video, but they actually move images in frames. So, like I said, in 10 seconds, we can have a 300 image stack forming a video, which is actually 30 frames per second. So it's just a combination of 300 images stacked together, which gives the illusion of movement, which is the video we see. So when we process these, we look at n batch size of t time frames, C for color channels, H for height, and W for width. This allows AI to see and understand motion. Next, let's look at the logic sets and rules. This is how we represent facts. For example, if it is a bird, it can fly. This includes knowledge bases and constraint networks for finding a solution that fits all rules. Now, this symbolic approach is great for ensemble sets, combining different AI models for better accuracy, and relational databases where we store structured information about entities. For operational structures, a heap helps us find the smallest or largest item instantly. A hash table allows for near instant lookups like finding a name in a massive digital phone book. Stacks, last in, first out, and queues, first in, first out, help the AI manage its tasks in order. So if an AI is exploring a maze, it might use a stack to remember the way back. Union find is a specialized structure used to track and merge connected groups efficiently. Now let's look at AI tasks and data structures. For search, we use trees and graphs. For machine learning, we use tensors and matrices. For reasoning, we use logic and rules, and so on and so forth. We must also consider efficiency trade-offs. Using a complex tensor for a simple task wastes memory, while using a simple list for a complex search might make the AI too slow. So to wrap up, we've learned how to recognize structures used across different AI fields. If you see a grid of numbers, think machine learning. If you see a branching diagram, think search or decisions. So thank you for your attention today. Please review these structures as they are the foundations for everything we'll build in the coming weeks. If you have any questions, please do let me know.